time for us to do some practice involving the root and ratio test, which is a great way to take a series and just say, look, let's try to understand the rate of growth of this series and be able to answer just by looking at the series itself what's going on. As with all tests, it takes some practice to get used to. How do you identify when to use it, and how do you carry out the computations? So that means do some practice. If you're following along with the video, make use of the pause button. See a problem that interests you, try it out yourself first. See how far you can get. And then if you need help, no worries, I'm here. You can just unpause me. And together, we'll figure it out. And as you do more, pretty soon, these will become fairly natural. You'll be able to say, aha, I see what to do, and I know how to do it. And soon, you're going to become amazing. Keep at it. You can do it. I believe in you. Well, let's begin. Our first problem. Determine whether the sum 1 to infinity of arctangent of n to the nth power over 2 to the n converges. All right. Well, okay, we're looking for, does this converge or diverge? What are some hints about what tool we should use? Now, of course, we know today we're talking about root and ratio tests, so we're like, ooh, it's going to be one of those. But there should be certain things that hint about what's going on. Now, in our case, we look at this and say, oh, look, we see things are being raised to the nth power. So when we think about the root test, that's really great, because if I have things being raised to the nth power, the root test says take things to the 1 over nth power, and they undo each other. So oftentimes when you see exponents like this, it's a signal that says, ooh, you should strongly consider using the root test. So we say, okay, put it another way, just to emphasize what's going on here. So sum n equals 1 to infinity, and we'll just put everything inside here to the nth power, arctangent n over 2 to the n. All right, well, great. So we're going to look at the limit as n goes to infinity of a sub n to the 1 over nth power, where a sub n is the whole thing. So this is our limit as n goes to infinity of arctangent of n over 2 to the nth power to the 1 over nth power. And now we see why, when we see, things being raised to the nth power, raising to the 1 over nth power works great. We say, look, these undo each other. So this is really the limit as n goes to infinity of arctangent of n divided by 2. And now, well, we need to know a little bit about arctangent. And the question is, what happens to arctangent as we head to infinity? So as we go to infinity, what is arctangent doing? If you plot the arctangent function, it's approaching an asymptote. And what it's approaching is pi over 2. So as n goes to infinity, we get pi over 2 on the top. Of course, you have a 2 there. And so we get pi over 4. Now, great news, we have a limit. Woohoo! Nice! We're not quite done yet, because we have to say, what is this number? And in particular, how does it compare to 1? Because that's going to be the answer. So, is pi over 4 below 1 or above 1? Well, pi is about 3.14, which is below 4. So pi over 4 is below 1. We don't need to know how far below 1. We just need to know below 1. That suffices. And so, since it's below 1, that converges. So by the root test, we can say that the sum from 1 to infinity of arctangent of n to the nth power divided by 2 to the n converges. And we're done. Wow, amazing, amazing. But of course, what's really happening when we're doing things like the root test is we're saying, look, if you go way far down, it's behaving like approximately pi fourths to the n. In other words, it looks like a nice geometric series. So, well, great. Wow, this was fun. We should have more of these. And good news, we have more of them. We always have more problems to do. All right. So, our next problem. Does the sum 1 to infinity of 1.001 to the n divided by n to the 1,000 converge? Like, well, you might start by saying, well, what's the first term? Well, 1.001. All right. What's the next term? 1.001 squared is about 1.002. On the other hand, 2 to the 1,000 is huge. And you can imagine, even by the time you hit like n equals 10, the top barely has budged. And the denominator is so big, you're like, wow, we're running out of space to write all the digits. And so if you only go by the first couple thousand terms of this series, it looks like, wow, all the terms are super, super tiny, it's super small, and it feels very convergy. I know convergy is not a word, but it feels that way, right? It feels convergy. But be careful. It's not what happens at the start. What happens at the end? That's what matters. Okay, so what do we see? Well, we see we have exponential on top, polynomial on the bottom. Who wins the race? And we know the answer to that is that exponential wins the race. So let's do this with the root test, because look, there's something raised to the nth power, so we can apply the root test. So let's look. We have the limit as n goes to infinity of, we'll think of this as our a sub n, 1.001 to the nth power divided by n to the 1,000 to the 1 over n. Well, all right, that's the limit as n goes to infinity. Upstairs, well, the nice thing is n to the 1 over n. Okay, those cancel. So we're left with 1.001. Now, downstairs you have n to the 1,000 to the 1 over n. Now, another way to write that, whenever you have sort of an exponent to an exponent, is really you're multiplying the exponents together, so you can take it in any order. So we can say, hey, this is really the same as n to the 1 over n to the 1,000. Now, why do that? Well, because there's a couple of limits that we kind of have burned into our hearts, because they're so important, because they show up. And one of them is, hey, as you let n go to infinity, n to the power of 1 over n goes to 1. It's actually not so hard to show. Pretty straightforward. So we say, ooh, this part right here goes to 1. And of course, 1 to the 1,000 is 1. And therefore, that says our limit is 1.001, or 1 to the 1,000, or 1.001. Now, remember, when we're doing the root test or the ratio test, either one, it's comparing it to 1. Which side of 1 are we? Are we below 1 or are we above 1? That tells us whether we are going to converge if we're below 1, diverge if we're above 1. Well, that's definitely above 1. So, by the root test, we see, aha, this sum will diverge. I guess diverges if you want to make it proper English. Now, you could have used other tests. Whenever you have a root test and you have that the sum diverges, what it really means is that the terms get arbitrarily large. So if the terms are getting arbitrarily large, that says, oh, you could have just used like the divergence test. And you could. So if you came to this expression and you said, well, what's happening to this term as you let n go to infinity? Well, it goes to infinity or infinity. You say, okay, l'hôpital. And you're like, okay, still going to infinity or infinity. And you're like, l'hôpital. And it's like, okay, still infinity or infinity. L'hôpital. And you're like, oh. And like 1,001 times later, and your voice is like, whoa. You'll see it goes to infinity over a big but fixed number, which means that it blows up. So you could have done this by another method. It would be a little bit messy. It would have taken some time. This one is kind of nice and compact, and it's somewhat more elegant, right? Because we don't have to say, okay, and apply it again and again and again and again, you know. And here it's like, no, just do it once, and life is good. All right, well, great. Fun problem. We like fun problems. Let's try another fun problem. So, does the sum from 1 to infinity of 1 minus 3 over n to the power n converge? Okay, interesting. Well, of course, we see, it's to the power n, and therefore we're thinking root test. Root test, right? So, all right, great. So let's look at the limit as n goes to infinity of, we're going to take 1 minus 3 over n to the n. That's our term a sub n to the 1 over n power. We say, hey, fantastic. This is the limit as n goes to infinity of what? Well, 1 minus 3 over n. You say, well, that's easy. That's 1. Now, if we get 1, what does that mean? Does it converge or diverge? And the answer is, yeah, that's right. That's the answer. We don't know. This really means more work. So you have to remember, for the root test, similar for the ratio test, when you get 1 out, it doesn't mean you're done. It means, oops, the test is inconclusive. So you want to be a little bit careful. Okay, so how do we be a little bit careful? Well, the ratio test, root test, are basically out at this point. They might say, Steve, you didn't even apply the ratio test. Well, usually the root and ratio will give the same effect for all intents and purposes. So now we're left with thinking, what other tests do we have? And if we look at this, we might start to say, Now, here, this looks a little familiar with one of our limits, right? Because there's a handful of limits that we should know by heart. What one does that look like? Well, there's a limit which says the following. The limit as n goes to infinity of 1 plus x over n to the nth power is e to the x. And notice, what's our limit? It fills this mold for a particular value of x. So this looks like the limit as n goes to infinity of 1 plus negative 3 over n to the nth power. So according to this rule, this would be e to the negative 3. And now we're like, aha! And e to the negative 3 is less than 1, right? It is, but that doesn't matter. Because, wait, you have to make sure you keep track of what you're doing. Because there's some tests where it's like, okay, compare it to 1. There's other tests that says, okay, is it a positive number or is it 0, right? So what is this telling us? Let's make sure we understand what this means. Well, what it means is that the individual terms, see, this is like our individual terms. So our a sub n is going to converge to e to the negative 3. Now, the important thing about e to the negative 3 is it's not 0. It's a little bit above 0. It's not a big number. It's definitely below 1. But we don't care, because what test is being applied here? This is, you might call it the nth term test. You might also call it the basic divergence test. But what it says is it says, oh, look, your terms aren't going to 0. We say, since the a sub n does not go to 0, the sum has to diverge. So this is good. This is sort of a reminder of a couple things. One, there's multiple tests, so make sure you know what test to use. And the other thing is, make sure you keep track of what each test is saying, especially tests that involve limits, because there's the root ratio test involves limits in a particular way, the limit comparison test involves limit in a particular way, and of course the divergence test applies limits in a particular way. Keep them straight, because it's easy to start to sort of muddle them around and mix them up. And then we run into danger where we say, oops, wrong assumptions. We don't want that. We want things to work. We prefer to get the right answers. 4 out of 5 mathematicians recommend getting the right answers. All right. Next problem. Use the ratio test on the following sums. Okay, well, all right. So the ratio test, okay, let's say, we'll start with this one as our a sub n. So what does that say? We're going to look at the limit as n goes to infinity of the next term over the current term. That's the ratio test. Just say, what's the ratio of 2 consecutive terms? So that's the limit as n goes to infinity for the n plus 1. Everywhere where there's an n, put in n plus 1. So 1 over square root of n plus 1. Downstairs, 1 over square root of n, because that's just the term as is. Well, you can simplify this. This is the limit as n goes to infinity of, combine them all together, square root of n over n plus 1. And you can even make this clean. There's a couple ways to do this. One thing you can do is inside multiply by 1 over n on top and bottom. And now we see, aha, we get some nice things happening. The 1 over n, see, that's the only place where there's an n, and that goes to 0. So we end up getting the square root of 1, which is 1. All right, well, well, okay, that's that. Let's do this one now. And here, we'll call this a sub n, and do a similar thing, right? Limit as n goes to infinity, a n plus 1 over a n. Well, that's the limit as n goes to infinity of, well, 1 over n plus 1 squared divided by 1 over n squared. Okay, so far so good. A n plus 1, just everywhere you see an n, put an n plus 1, and then just copy it down. And then we can do a similar thing. So this is the limit as n goes to infinity. If you imagine flipping the bottom up and putting it all inside, you get n over n plus 1 squared. Well, that's the limit as n goes to infinity of 1 over 1 plus 1 over n squared. Same idea. Multiply top and bottom by 1 over n inside that square, which is 1. Now, we're kind of done, but what's the point here? The point here is that in both cases, we got 1. But what does that tell us? Well, notice the first sum. It's a p-series, right? This is a sum which is going to diverge, because you have p equals a half, which is less than or equal to 1. This is also a p-series, but now p is 2, which is greater than 1. So this one is going to converge. And so this emphasizes why, when we get 1 out at the end, we can't make a decision. That's what we're trying to learn here, is you just don't know. Because there are cases where the limit is 1, where it converges, and there are cases where the limit is 1 and you diverge. So be careful. Make sure you pay attention. And whenever you get 1 out, what it really means is more work, more work. All right. Well, it's good to keep track of that, right? It's good to know when there's more work to be done. All right. Well, let's try another problem. So here we go. Determine whether the sum from 1 to infinity of 3n factorial over 7 to the n times n factorial times 2 to the n converges. What? Now, this will be interesting. And all right, there's something about this problem which is telling us, hey, you've got to use a particular method. And what there is these factorials. Whenever you see factorials, factorial means ratio. It's the only test that we can use. And the reason that the factorial really needs to use the ratio test is because we don't have a nice way to think of factorial in terms of like a continuous function. So things where we talk about like limits as we head off to infinity, and we're looking at like a factorial to 1 over n, like, what is that? We don't have the tools to answer that question yet. I don't want you to think that it can't be answered. It's just we don't have the tools yet to answer that. So we're like, great. So ratio test it is. All right. So here we go. And we're just going to be patient. All right. So we're going to take a look at the limit as n goes to infinity of the next term over the current term. Now, when you're doing the ratio test, one of the hard things is to make sure you get the next term written down correctly. So here's a tip for all of you following along. Parentheses. Parentheses are your friends. When in doubt, be generous with your parentheses. So, when we write down the a sub n plus 1, what we'll do is we'll just, everywhere where we see an n, we're going to put n plus 1, and we're going to use our parentheses just to make sure we don't lose anything. So 3 times n plus 1 factorial, 7 to n plus 1, n plus 1 factorial, 2 times n plus 1 factorial. So that would be a times n plus 1. Sorry, excuse me, a sub n plus 1. All right, now, what about a sub n? Well, it's just, there it is. Now, since we're dividing by it, it's the same as multiplying by the reciprocal. So I'm going to go ahead and multiply by the reciprocal. 7 to the n, n factorial, 2n factorial, divide by 3n factorial. Now, at this stage, let's sort of group things together. So, what can we do? Well, we'll take a limit as n goes to infinity. And here, well, this is really, if we think about distributing, that's really 3n plus 3. So I'll think about it as 3n plus 3 factorial. And then downstairs, I'll match that with the 3n factorial. So these seem to be fairly similar. What else do we have? We have a 7 to the n. Okay. Downstairs, there's a 7 to the n plus 1. Here's an n factorial. Well, that matches pretty well with the n plus 1 factorial. And here's a 2n factorial. And that's matching here. Again, distribute. That would be 2n plus 2 factorial. All right. Now, we're going to do some careful expansion. How does this work? Well, the way this works is, imagine you have a factorial, and we're just going to pull off the first couple of terms. Because how do factorials work? Well, let's do this 3n plus 3 factorial. We'll do it long form just to emphasize what's happening, and then we'll go through and do the rest fairly short. So when we think about 3n plus 3 factorial, well, what we have is, what that means is you start with 3n plus 3 times 3n plus 2 times 3n plus 1 plus, times. Okay, so you're really multiplying all the numbers starting from 3n plus 3 all the way down. So you can think of it as 3n plus 3 times 3n plus 2 times 3n plus 1, down to, well, actually I'll do 3n all the way down to 1. Now, there's a couple ways to think about this. For us, we say, oh, there's a 3n factorial downstairs, and hey, what do you see? You see a 3n factorial on the end. Like, great. So what you really have is you have the first terms here, 3n plus 3, 3n plus 2, and 3n plus 1, and then times by 3n factorial. So we're pulling off terms. And there we go. Another way to think about it is to say, all right, in general, if I have a factorial, I can pull off the first term. So that'd be 3n plus 3, and times it by everything that's left is the factorial starting 1 down. So 3n plus 2 factorial. So I can pull off the first term. And now I'll just sort of get into the habit, pull off terms as I need it until I say, aha, and now it matches with what's on the other side. Either it matches above or matches below. So, for instance, here we have, this is the limit as n goes to infinity. Now, I'll see the top is bigger, so I'm going to keep pulling off terms until I get down to 3n. So 3n plus 3, 3n plus 2, 3n plus 1, 3n, and now I say I stop, so 3n factorial over 3n factorial. Here, 7 to the n, or 17n plus 1, all right, well that's 7 to the n times 7. Next term, okay, pull off a term of the n plus 1 factorial downstairs, so n factorial upstairs, n plus 1 times n factorial. And downstairs, again, pull off the 2n plus 2's, so we're going to have a 2n plus 2, a 2n plus 1, and then 2n. Great. And then upstairs, 2n factorial. Now, what's happened? Well, if we've lived a good, clean algebra life, things should simplify. The 3n factorials, nice. 7 to the n's, nice. N factorials, really great. 2n factorials, wonderful. Woohoo! Life is good. We've made amazing progress. And in fact, look, all the factorials are gone. Okay, so what do we have? Well, this is the limit as n goes to infinity. We have 3n plus 3, 3n plus 2, 3n plus 1. Everything else got canceled upstairs. Downstairs, 7, n plus 1, 2n plus 2, 2n plus 1. Okay, so that's where we're at. And now it's polynomial over polynomial. And you can do things like, oh, look at the leading coefficient. Another thing is say, well, look, let's just divide 3 terms by 1 over n upstairs, 3 terms by 1 over n downstairs. So I'm essentially multiplying by 1 over n cubed, both upstairs and downstairs, which will have the effect of slowing things down so things don't go off to infinity. And if we do that, we'll see, lo and behold, nice things will happen. All right, so now we're ready to ask, what happens as we go to infinity? And we look at it term by term. We say, okay, well, everything with the something over n goes to 0. And wow, beautiful. It's almost like it was meant to be, because I think it was meant to be. And what do we have? Well, we have 3 times 3 times 3, which upstairs is 27. Downstairs, 7 times 1 times 2 times 2. Well, that 7 times 2 is 14 times 2 is 28. 27 28s. Wow. Now remember, what do we care about? 1 is the threshold. 27 28s is really close, but that's okay. We can definitely make a decision. Are we below 1 or above 1? We're below. This is less than 1. Okay, so the conclusion is, since the ratio of these terms as we went to infinity is below 1, we can say by the ratio test, the original sum will converge. Good, good. All right. You notice, very close, very close. It wouldn't take much to push it over the line. So sometimes it's a little delicate. You got to keep track. But you'll see this very consistently when you see factorials. You'll say, okay, we're doing a ratio test, and it's like, okay, pull off the first couple of terms, until you can get the other parts of the factorial to cancel. And once you get the hang of it, it actually goes pretty smoothly. And it can be, dare I say, even a little bit of fun. All right, good. That was a nice one. I like that one. Well, let's do one more problem. One last problem to finish it up. Determine for which values of r greater than or equal to 0 that the sum k equals 0 to infinity of k factorial squared r to the k over 2k factorial converges. All right. Well, let's think about this and see if we can figure this out. Okay. Well, we see factorials, and as soon as you see factorials, you know that means that we're going to have to do a ratio test. So we say, all right, let's think of this here as our a sub n, and we look at the limit. N goes to infinity of a sub n plus 1 divided by a sub n. And we want to get an idea, well, what does this do? Is it smaller than 1? Is it bigger than 1? And that answers the question. So we say, all right, that's the limit. N goes to infinity. Now putting it in here, now of course this says a sub n, and it uses k, it doesn't really matter. So we're going to put in here n plus 1. You could use k's, by the way, it doesn't really matter. It's just all, these are all sort of, you might call them dummy variables. So n plus 1 factorial squared r to the power n plus 1. Divide that by 2 times n plus 1 factorial. Okay, divide by a sub n, same as multiplying by the reciprocal. So that'll be 2n factorial divided by n factorial squared r to the n. Well, now we can do a couple things. Note this n plus 1 factorial squared, we can pull off a single n plus 1. So we can think of it as n plus 1 times n factorial squared. And then downstairs we have an n factorial squared. All right? This r to the n plus 1, downstairs we have r to the n. And then this 2n factorial, well, downstairs it's 2n plus 2 factorial. So 2n plus 2 factorial, I'm going to pull off the 2n plus 2, I'm going to pull off the 2n plus 1, and then it'll be 2n times 2n minus 1 times the denominator. In other words, from then on, everything can be compressed into the 2n factorial. So, all right, there we go. Now, if this is a good problem, things should simplify. We see, aha, the n factorials cancel, the 2n factorials cancel, and we can cancel off a lot of the r's. So, what do we have? Well, we have the following. This is the limit. As n goes to infinity, we have an n plus 1 squared, then there's an r, and downstairs we have 2 times n plus 1, whoops, right, because it can factor out 2 there, times a 2n plus 1. Yep. So you can even cancel off an n plus 1. Okay, so this is the limit as n goes to infinity of actually something really simple. It's r times n plus 1 divided by, downstairs we'll have, well, you can write this as 4n plus 2. Okay, good. Now, what does this go to? Well, you can multiply top and bottom by, say, 1 over n. So you have r, 1 plus 1 over n, over 4 plus 2 over n, and it goes to r over 4. So, that's the limit. Now remember, we haven't said anything about r. We just said, for a given choice of r, here's what happens in the limit. But now we have to say, well, what do you do? You see, there's three possibilities that we have to explore. What happens if we're less than 1? Well, this is going to converge if we're less than 1. If we're greater than 1, this will diverge. And if we're equal to 1, we don't know. So what do we see? We see, r over 4 less than 1. So this says r less than 4. Sorry, if r is less than 4, r 4 is less than 1, we converge. If r is greater than 4, then r over 4 is above 1, we diverge. And now we come to the conclusion that if r equals 4, we don't know. Ooh, boy, this is, we were so close. We were so close. Okay, What has happened here? Well, essentially, see, we only care about r greater than or equal to 0. So we only care starting at 0. And we've now said that after 4, you're out. You're going to diverge. Between 0 and 4, you're in. You're going to converge. But what we don't know is what happens at 4. And he says, you see, it says determine for which values of r greater than or equal to 0 that it converges. We have to come to some kind of conclusion about 4. And so now we look at it and say, oh boy, this is going to be interesting. How do we make our decision? Does 4 converge or does it diverge? Okay, well, let's step back a little bit. Suppose we look at this part here when r equals 4. What do we see? This is 4n plus 4 over 4n plus 2. And that's not too surprising. What can you say about the quantity of 4n plus 4 divided by 4n plus 2? We can say something. What can we say? Well, the numerator is larger than the denominator, which means that this is above 1. Okay, how can we use that? Well, where did this come from? You see, if you wind it back, it turns out that this is our ratio an plus 1 over an. So, what is that telling us? Well, it tells us that we have a great aha, and this doesn't always work, but sometimes it helps to sort of look a little bit. And our great aha is to say, wait a second, an plus 1 is bigger than an. Okay, so what does that mean? That means that our terms can only get larger. Well, if our terms are getting bigger, what aren't they doing? They're not going to 0. To go to 0, we need to get small. So once we know our terms grow, we say this says that our terms are growing. We're not claiming that they're growing off to infinity. We're just saying that they're growing. And so our conclusion is a sub n does not go to 0. So if that's the case, if a sub n doesn't go to 0, what do we know? What we can say here is this r equals 4 will diverge. And this is our nth term test, or some people call it the basic divergence test. So this is in fact the right picture. It will only converge, so our final answer is 0 less than or equal to r less than 4. And those are our r's where we converge. So we don't converge at 4, we don't converge past 4. And that's it. Wow. What a problem, huh? What a fun problem. Now this sort of gives us a foreshadowing of things to come, where we ask ourselves the question, well, when do particular things converge or diverge? and sort of when is there some sort of a threshold between convergence and divergence. So we're going to come back and revisit these ideas again. So yay, woohoo, get to do things like this some more. Something to look forward to in the future. But for now, thanks for coming, and hopefully you had a good time, and we'll see you again later. Bye.